Let's do next week.
Okay, so we're going to edit our card.
Or finish the negative. Okay, good afternoon. Let's start actually. Okay. Yeah.
Yeah. I have to finish my course every night.
I mean, that's what I'm saying.
I'll try to finish it.
Okay, so we're going to...
Try to get it done.
Like this? Yeah. Okay, so let's look at new type of machine elements now. Okay, this is basically about design for welded joints. So hopefully we can finish today or a little bit next lecture. Okay, and then our last component of the class will be spring designs. Okay? And then the last lecture we'll just use some time to do a quick review, and then that's it. Okay. Alright, so basically what is the objective here is to study welded joints, and for the first part I'll give you a very short introduction on the welded joints, and we'll look at basically welding symbols and some terminology associated with that, and how do we communicate with other people, okay, from these specifications here, okay, in the engineering drawing. Most important part of this objective here is to learn how to calculate stress on welds and welded joints, and also the strength of the weld, basically based on the strength of the welds and the pairing materials. Okay, so that's what we typically do. Okay, so we have to analyze the safety of these machine elements. In this case, here is the welded joints. Again, this is the diagram we have seen many times, and as you can see, this is basically we're here. Okay, we're at the support the mechanical generated loads, so welded joints, okay, just like what we just finished the fasteners. Okay. Okay, so a couple definitions first. Okay, and then we'll use my OneNote to go over some specifics, other things, but first some simple definitions. Welds, joints, and weldments. So what are the definition for each one of these here? Okay, so well, for weld, it's basically referred to, it's a zone of metal that joins two or more components, okay, created by localized melting, mixing, and cooling of material from the pairing components and an expendable feeder metal of a compatible composition here. Okay, as you're going to see it later, I'll just shortly going to introduce the different kind of welds. So basically, you will see that when it comes to welding, it's always basically a coalesce of the pairing material and also the feeder materials together. Right, and the melting is accomplished using a heat source, okay? And this heat source sometimes mostly is generated by electric arc or oxyacetylene flame. So that's weld, okay? And joints, the definition is, it's a configuration of apparent components defining a gap to be filled by a weld. As you're going to see, there are different types of joints, okay? And one of the most common type of joints that you will see is basically called T-joints, which is this one here, okay? So weldment, that's actually a bigger type of concept. It's a structural component constructed by welding several components together. So that's weldments. Okay. So let's show a couple examples of it here. This is basically, we'll give you an example for weld and joint example. So you have basically two steel bars that are here. You want to join them together, and to join them together, this is what we call basically, it's a T-joint, because it's a T shape right here. Okay. And you apply basically the welds, okay, at this location and at this location, and also on the other side and bottom here. Okay, so this type of weld, actually later we'll learn, is called the basically called the fillet weld. Okay, this is to give you an example here, right? And you can actually have a different type of joints other than the T joints, right? I'll show you a couple pictures later. Okay? And this one is an example of weldments. Okay, this is basically a digging machine. Okay, and if you look into the structure of the digging machine here, so there are weldings almost everywhere. Okay, for this basic structure, there's weldments here. Okay, and this weld at here. Okay, and so that's basically what really the definition for weldments at here. Okay, it's a structure and putting together, okay, by the welding at here. Welding process. Okay, so this is a very basically college type of things you will practice. Okay, and if you take a technology diploma. Okay, the most common type is arc welding. Okay, so when you use arc welding, it's basically using a welding power supply to create an electric arc between electrode and the base material. Okay, so the electric arc will generate very high temperature and heat, so which will melt the metal at the welding points. Okay. There are category-wise, okay, there are two different categories we can use, okay, to talk about describe the welding process. One of the categories, the so-called consumable electrode method. Okay, so basically, as what it suggests, the electrode, okay, which I'll show you what it is, basically, is consumable one. So it will be used up, and then you have to change it to a new one, right? Yeah. And non-consumable electrode methods. Okay, so that's basically the one we're going to look at called gas tungsten arc welding. Okay, so you have a essentially non-consumable electrode there, or made of a tungsten. Okay, so that's the two huge categories here: consumable and non-consumable electrode methods here. Okay, yeah. So let's take a look at a couple examples here. First, for the consumable ones here. Okay, so this is called the sheet metal arc welding. Okay, sheet metal arc welding. Often in time, this is also called stick weld. Okay, this is actually the most common type of weld in industry. Almost 50% actually use this type of weld. Okay. So you probably have seen that quite a bit. You know, basically you're like holding a stick, okay, and the stick essentially refer to the electrode right here. Okay, yeah. So the electrode needs to be selected appropriately to match the base metal, okay, which is basically the metal that you're welding at here. Okay, so match the property of that, which we'll see that later. Okay, yeah. So you will connect certain power source, okay, to the electrode, okay, and then as you kind of just like lighting up a match. So as you go over the surface, okay, go over the surface of the metal, okay, and there will be arc essentially generated between the electrode and the base metal, okay, and then the arc will continuously generate very high temperatures. Okay. So the high temperature will melt the base metal and also the electrode at the same time, and then all together, so you have a melting pool of metal over there. Okay. And that pool of metal, it consists of both the base metal and also the electrode materials, right? Yeah. The electrode that here are covered by some kind of a material called flux. Okay, so the flux will also be melted, and the flux when it melted is actually generate some kind of carbon dioxide here. Okay, yeah. So the purpose of the flux is basically to protect the metal from oxidation, essentially. Okay, at the high temperature, it's very easy to oxidize. So that's what basically the flux does. Okay. So overall, essentially, as you finish the process, right? As you finish the process, and you actually will see a thick, basically kind of a dark material, right, left it on the surface of the melt over there. So it's called a slag. So basically, you're going to have to scrape it off and then to clean it up. Okay. So that's actually one of the shortcomings for the stick welds right here. Okay. But it's very useful because you can use it, okay, almost in any type of situations, especially in outdoor application. Okay. If it's outdoor, even as the windy situations, you can still use this stick weld. Okay. If it's gas type of weld, you actually can use that because the wind will blow the gas away, right? Yeah. So that's stick weld here. Okay. Yeah. And this just different picture here showing the process of doing stick weld here. So that's the slack that we had to screw it off at the end of the process. Okay. The other type is called the gas metal arc welding. Okay, so gas metal arc welding here. Okay. So it's also can called MIG, so MIG weld. Okay, so they're typically called the MIG weld. Okay. So what happens is it uses a wire electrode. So it uses a wire electrode at here. Oh, sorry, where's wire here? So this is wire electrode at here. Okay, instead of that electrode that you used in the TIG welds. Okay, so the electrode at here doesn't have the flux covered on the surface. Okay. So then what you use is you use some sort of inner gas, okay, feeding into with the wire at the same time. Okay. So the inner gas could be argon or helium, so that basically to displace the air, okay, at the welding location to do the similar type of purpose, protecting the welded joints essentially. Okay, yeah. So that's gas metal arc welding at here. Yeah. This is a similar picture as the other one, just a little bit better illustrations of the different components for the gas metal arc welding. And the other one, as I said, is non-consumable. Basically, in this case, the two previous cases are consumable one, and this is a non-consumable. Okay. So the gas tungsten arc weld, you have essentially an electrode, okay, which is made of tungsten at here in the center, okay, and that's not going to be like consumed as time goes on. And you do need basically a feeder material at here to do the welding. Yeah. And this typically will generate a fairly clean surface after the welds at here, okay? And especially used for non-ferrous metal. Okay? So that's gas tungsten arc weld. Okay? It gives a very clean weld. Okay? But at the same time, it does have a limitation, which is the wind, right? So you feeding the inner gas. Okay, if it's outdoor, then it might not be very applicable. So let's take a look at different types of welds at here. Okay, as I showed you already one type, which is a T-joint, and there are certainly many other different type of joints at here. So as you can see, this is so-called the butt weld. Okay, and this is called the corner weld. Okay? And this is called the lap, and this is called edge, and the center one is the T-joint. Right. So there's different types at here. You do the welding, you select the joints. Based on the different type of situations. Okay. And this is another picture, just a little bit cleaner illustration of butt weld, okay, and the fillet weld corner, and this is called the flange joint, right? Yeah. Okay. That's type of weld. Okay. Type of joints. So how about the type of welds, right? You know, we showed actually one already, the fillet weld, the T-joint. We showed the fillet weld here, and there's certainly different types here. So this fillet, there's also the bead type. Okay, this is the bead type of welds. Okay. And then you can have a so-called the plug or slot type of welds at here. And you can also have a so-called the groove welds. For groove welds, it really depends on the shape of the weld. There's square, there's double V, there's U, there's J type, right? So this is U, J. So there's basically based on the shape, you have a different type of a groove welds here. Okay? And the last type, there's another one called spot weld. Okay? And this is a very common in automobile industry. Okay? And it's usually done by robots. So you have a robot basically trying to weld two metal sheets together, okay, and the high current go through basically the two metal sheets, okay, and then the high current will melt the metal at the one location there, okay. And just continue, you know, basically there's different type of a bevel, the groove welds is a bevel groove, V groove, okay, and let's see the difference, right? You know, basically this is one the V, which is one side of V, and then you have here is like a two sides of V here, and there's also like a degrees of angle degrees requirements, right, in terms of the shape. Okay. So, and this is actually what we're going to learn next. That's how we can actually denote that type of welds that are here. Okay. So you see, if you have two plates and you want to weld together, if you use this symbol, that's what we're going to learn next. And that basically means you're using a bevel type of groove and a certain shape and a certain angle, right? It's all indicated by the symbol here, right? And similar like this one, here and here. Okay, this is all the different ways of denoting the type of welds. Same thing for J and U. Okay, so that's the symbol associated with the J groove, and the U, and this symbol associated with the U groove. And which is actually exactly what we're going to look at essentially, and the typical standard for weld specification. Okay, so weld specification. Weld specification, in general, it's defined by the American Welding Society. So the American Welding Society defines how you denote the specification, right? The specification includes a number of parameters like the type of welds, the size of the strings, the root opening, right? So basically that how you open it, the throat, the depths, welding process, okay, even, and also numbers, spot welds, length of welds, finishing, groove angle. So those are all can be specified on the drawing, okay, basically. Okay. Yeah. So how do we specify them, right? This is how you can do it. Let's say you have a welding joint at here, or joint at here. So what we do is basically we draw a horizontal line and then an arrow pointing to certain location. Okay. Now for this horizontal line here, this is called the reference line, and you can label or you can sketch some sort of notations on the top or on the bottom here. So you can do something either at the top or the bottom. Okay. Now, if you do it at the bottom here, what it actually means is it's on the arrow side. So, for example, you have something labeled here or some symbols sketched here. What it means is it refers to the arrow side. Okay. If you put it on the top here, then you actually refer to what? To the opposite side of the arrow that pointing to. Okay. And if you have the things show up on both sides, then it basically means both sides. Okay. And then often in time you probably, especially when you're welding a metal tube, okay, then you're making all around welds. So that symbol here, it refers to what it means here, basically all around welds. Okay. And that big dot actually is a slightly different symbols here. Sometimes you put a little bit of flag at it here, okay? A little flag notation. That means basically it's a field sign. It's a field symbol. Okay. So that's what I summarize here. So reference line, and the arrow connections to the reference line here, and the symbols, okay, should be entered either in the top or the bottom side. Okay, so here are the examples that what symbol that you can use, you can put it, okay, on the top and the bottom of the reference line. So as you can see, the first one here is the groove weld type symbols, right? They're different groove type. And the bottom here, those are the fillets. So when you draw a triangle, that basically means the fillet weld. Okay, and when you draw a horizontal, sort of like a block rectangle here, that basically means the plug slot. Okay? When you draw a circle, it means it's a spot weld. So that's how you interpret just by looking at the symbols that are here. Okay. Yeah. So let's take an example here. Okay. Yeah. So for example, you have a T-joint here, and you want to weld. You want to have a fillet weld on both sides of the T-joint, right? Yeah. So what do? Technically, you should draw this one here over here. So basically, put arrow over here and then horizontal line here, and then you can see here you have triangles on both ends, right, on both sides of the reference line. So that basically means you have a fillet weld on both sides, right? there's also number 5 at here. So that's a very important parameter. That's very important information. You will need that for your calculation later, and I'll explain what this is. The 5 at here basically refer to what we call the leg size. Okay, the leg size, and we'll come back to this. Okay, so leg size for now, you can remember the leg size refer to the height. Okay, the height on the either side of the triangle here, so they're symmetric. So this is basically the height here is the leg size. Okay, yeah. And you see this one here, this is basically welding a metal tubes onto another member. Okay, then what we want is we want an all-around weld, right? So and we also want a fillet weld. So you don't need to put triangles on both sides, the top or both sides of the reference lines. Because one side is good, but then you use a circle at here, right? So that refer to all-around welds at here. Is that good? Yeah. And the bottom here, okay, you can see this is slightly different now. So you have an arrow and the horizontal line, reference line. Then you got a triangle on both sides of the reference line, but then they kind of separate from each other a little bit, right? And there's a number saying 60 to 200 basically. Okay, so this is exactly what happens at here. Basically what you have is you have a sort of spread it out welds. Okay, so not a continuous weld from one side to the other side. Then the 60 at here basically means that's the length of each segment of the weld. And then 200 means it's the interval between two adjacent welds at here. Okay, so that's how you can interpret this one. Okay, so let me give you an example now. Okay, so based on what we just learned, okay, here are 3 different type of welds, right? Here are 3 different type of welds that are here. Okay, see the 3 different type of welds. That's basically what you want to do, right? Okay. And correspondingly, right, you look at the bottom here. Okay, this is how basically you want to, if you read it from the drawing, and this is basically how you want to finish the weld at the joint. So here says 125, 75. So basically means I don't see the other side. Basically means what? I have 125 lengths of welds, fillet welds on here, and on the other side of the joint here, there should be a 75 right here, right? Yeah. Same thing for this one. There is 80 and 124. 80 is the length. 124 is the interval between the two. Okay. Here's 60 and 20 here. Okay. So what would be the welding symbol then, right? How would you draw the welding symbol for in each one of this one here? Okay. So the welding symbol basically means using what we just learned. Basically I have a horizontal line. How do I indicate the fillet weld for this one, for this one, and for this one, essentially? Okay. Yeah. So I'll show you what it is right here. Okay. So you see, this is how you would indicate 125 and a 75. So you point to here. So the arrow side, you see the arrow side. Remember which the bottom or the top refer to the arrow side? It's actually the bottom, right? The bottom refer to the arrow side. Okay, yeah. So I mean the orientation could be different, but if you have a specification like this, then you should know on the arrow side is 75, the other side is 125. Okay, yeah. And then here you have a fillet weld, so 60. So both sides the same thing. Both sides the same, so it's basically 60 to 125 here. Okay, And then this one is different because they alternate, right? So this one here, they alternate on the both sides. So that's why the two triangles are sketched, okay, not on top of each other essentially. Okay. Yeah. So here's my expectation. If I give you one specification, right, you should be able to identify what type of weld that's going to be executed. Is that clear? Yeah. So that will be a multiple choice question. Okay. Yeah. It's hard to say it here. Yeah, sometimes you save material, sometimes you save your cost, whatever, right? Yeah, but here this is just simple illustration of how to match the specification to the type of action essentially. Yeah. So yeah, if you have a really long joint, right? And if your analysis shows you don't really need to weld all the way from this end to the other end, right? Then you don't need to, right? So that's actually part of the analysis essentially, right? So how long the weld should be. Another analysis is how high the lag edge should be, right? That's part of the calculation that we're actually gonna show there, right? When you have a joint you wanted to weld, and you decided to use a fillet weld, then what will be appropriate lag height H, or what will be appropriate lengths of the welds at here, right? Good. This is another example. Essentially, it's from an actual welding drawing. Okay? As you can see, you will see similar basically symbols that we see before, but the difference is there's one bit of difference here. You see this one here. There's a little bit of flag. So that flag actually shows this is a field symbol. Okay. Yeah. So it should be done in the field. That's basically what it means. So those are very short introduction to the welding symbols. As I mentioned, for this portion, my expectation is to where'd they go? So just a sec. Is to be able to identify, to map appropriately, okay, between the symbols, the specifications, and the welds. Okay, so let me go to the next topic here using OneNote to write. Okay, yeah. So in the next portion, what we're going to do is, so we're going to focus on the safety of welded joints. Now, in order to talk about the safety of the welded joints here, and I have to go over basically two parts. Okay. So one, as everything basically what we learned before, we learned certain machine elements. So what we do is we have to look at the stress, right, exist at a point, and we also have to look at the strains, and then you compare the stress and strains, so you determine basically the safety at here, right? Yeah. So that's essentially the idea what we're going to approach at here. Okay. Yeah. So first, maybe a couple of definitions at here, just to be clear before we move on at here. Okay. Yeah. And I showed you the type of welds already. Okay. There's a butt weld, there's a groove weld, and there's also fillet weld. Okay. There's a very important concept. It's called throat and throat area. So, for example, right? Let's take a look at this type of welds at here. Okay. CJP basically means completely joint penetrate, and PJP meaning partial joint penetration. Okay, so you're welding two pieces of metal together at here, and when you finish, and the welded joints will look like more or less like this. Then at this location at here, there's a very important parameter called the throat. So this throat T. This is parameter T at here. That's actually a parameter very much related to the way we're going to calculate our stress. Okay, and the throat is essentially the thickness. You see the thickness of the regional members at here. But this is not the thickness of actually the welds. The welds, there's a little bit so-called reinforcement, right? A bulge at here. Okay, and adjacent to basically at the area. So at the area between the member and the weld or the electrode. So this is what we call the fusion area. Okay, so this is the fusion area. And if you look at the fillet weld, we have a similar basically definition at here. So there are two fusion areas on each side. So that's a fusion area. Okay, and then you also have the throat. So the throat at here, basically, if you cut a 45-degree, and this length here is called the throat. Okay, and also this is the leg edge. So the fillet, which is what we're actually going to focus in this part of the lecture, two important parameters. One is leg edge, and the other is the throat at here. So this thing is inevitable that we have to deal with when we do our calculations. Okay, so let's look at the stress. Right, first let's look at the stress. Okay, on the weld or welded joints. Okay, and I'm gonna start with the simple one at here, okay, and then we'll look at the fillet weld type of the T-joint, the fillet with stress within a fillet weld. Okay. So let's see if I have a situation like this. So you have basically two plates. Okay, you have two plates. You're trying to weld just like this one here, right? Yeah. So let's say you're trying to weld it in together here, right? Trying to weld it up. Okay. Yeah. So and then if you have a force, okay, acting on both sides of this weld, okay, these welded joints at here. Okay. So how do I calculate the stress, or what type of stress existed, right? Yeah. So this one is actually fairly straightforward. Basically, what you do is, okay, you look at the cross-section area. Okay, so you look at the cross-section area at the throat location. Okay, at the throat location here. So this is basically the so-called the throat. Okay, so let's call this as T at here, right? Then you can imagine if the plate has a length L, then the stress at the cross-section area, okay, the throat area, will experience what? A normal stress, right? So that's basically F over T times L. Okay, that's a normal stress for this type of situation. Okay, yeah. If what you have here the same joints, okay, if this is the same joints at here, okay, if the same joints at here. Now the difference is, let's say, okay, is that you have a force actually going like this. Okay, a force going like this. Instead of a pulling or pressing, you have a shear force essentially. Okay. Then for this particular case, what you do is you do very much the same thing. You also look at the throat area. Okay, so you also look at the throat area, which has a throat T. So the throat area is basically the cross area, okay, at this location, right? Cross area. And then in this case now, what you have is a shear stress, and the shear stress, the formula-wise, it's the same as that normal stress there. Okay. So if you have a stress like this, then then you calculate if you have a joint like this, which is the butt joint. So this, I will call it, this is a butt weld, right? Then you calculate the stress using the two simple formulas. Okay. So as I said, the emphasis actually on the next part, which is, let's look at the stress in fillet welds. Okay. Yeah. So let's look at the stress in fillet weld. Okay. So what's a fillet weld? Basically, let's draw something to illustrate the idea here. Okay. Let's say you have two plates, or even three plates, and you're trying to join them together, okay, at this location. So what you do is basically you can apply a fillet weld, okay, and to join these members together. Okay. Now suppose we have a leg height at here h. So this h here is called leg height, right? So h is the leg height. And consider a loading condition, for example, like this. So you have basically two forces on one end and then one force on one end on the other end, and which is in balance. So that's the type of loading condition here. Okay. Yeah. And now I can also label and one more thing here, which I will use in the next. Okay. Which is, let's label the throat T. So throat is, in this case, you cut a 45 degree, basically 45 degree line, and then that length is basically called T. So it's a 45 degree line, okay? A 45 degree cut. And this is called throat T, right? Just like the definition what we have here. Okay, so now the question basically, as I said, is to figure out the stress, okay, in the fillet welds here or here. First, what I will do is I'll do it very analytical way here. Okay, so do it analytically to derive a certain stress, okay, within the within this fillet weld. So analytical approach. Okay, so analytical approach. So what's an analytical approach? So analytical approach basically means that this is what we're going to do. Okay, we're gonna cut cross section. So we're going to cut a cross section anywhere. Okay, anywhere inside this fillet weld. So it's like I cut it. Okay, it's like I cut it with a theta angle. It's not necessarily 45. Okay, just cut it with a theta angle here through that fillet weld. It's okay? Yeah. So if you do that, let's take out that cut here, and basically what we have here is like this now. Let's say this is my member here. This is 1, 2, 3. So let's say this is member 1 and here. Then after the cutting of after cutting it here, so this is a theta angle, right? So we do the cutting at here, okay? And this side is H at here, okay? So explode as H, and that's the cut theta here, and here's your F, okay? Now once you do the cut here, imagine, right? So this is basically, this is a cross section, isn't it, right? So here you have a cross section here. Okay, so here a cross section. You cut it through the joints, right? The joints. So I can label some free body diagram in here. Basically, let's say I have a force pointing this way, call it Fs here, and a force normal to the surface, let's call it Fn at here. Okay. Yeah. Now this angle, okay, is still 45 degree. Okay, the top one here is 45, so that's that 45 degree over there, right? Okay, so that's basically how you cut it, assuming on that cross section you have a force Fs and the normal force Fn, right? And then let's just look at the cross section now, right? Let's just look at cross section here. So technically, if I draw the triangles out a little bit, it's like this. So basically, here's a theta angle here, and here's H. Okay, here's H at here. Let's say if I call this as the T star, so the length here is T star. Okay, so suppose I call this a T star right here. Now, if I want to calculate the stress at the cross section area, then what do I have to do is I have to get the T star first. Okay, yeah. So mathematics, what you can do is basically you use a basically triangle trigonometry property. So T star over the sine this angle here. So this is 45, and that equal to this angle, the H, over sine this angle, which is 180 minus 45 and minus the theta, right? That's trigonometry identity. Okay, yeah. Then I can actually solve for T star, okay, based on this expression right here, which turned out to be H over cosine theta plus sine theta. Okay. So that'll give us the T star value here. So once we get the T star now, then I can calculate what is the shear area, basically the shear area A, and which is T star times L, right? So total, basically the total length L. Okay, so this is T star at here, right? And then times L, you get the shear area, which is H over cosine theta plus sine theta, and then times L. Okay, that's a shear area A. Okay, good. Once you get the shear area A, then we'll be able to calculate Fs and Fn, and then we can calculate the stress associated with Fs and Fn here. Okay. As you can see, if you want to maintain the system in equilibrium, then there gotta be a relationship between capital F and Fs and Fn, right? Yeah. So for equilibrium, your Fs should be F times sine theta, and Fn is F times cosine theta. That's to maintain equilibrium here. So now I can calculate basically the stress due to Fs. So shear stress on area A, that'll give me tau equal to Fs over A, which is formula. Now you can simplify that and then end up with F sine theta cosine theta plus sine theta square and over H times L. Right, so that's the shear stress caused by the Fs at here. And similarly, you can calculate the normal stress, okay, on this area A, which is caused by Fn at here and over A. And that gives us a very similar expression. So sine theta cosine theta plus cosine theta squared divided by HF. Okay, so that's very analytical, you see, right? So we have mathematically did an arbitrary cut, and then find the equilibrium force, find the cutting cross-section area, and then find the stress associated with the two forces. Okay. But this is arbitrary cut due to a certain angle theta at here. Okay. So now the next basically portion is we actually wanted to interested is, so what will be the maximum value here, right? Or which angle theta will give us the maximum value here? Okay. Now before we going on here, another thing we can do is, okay, if you recall in basically for this theta here, if you recall in the static analysis, what we do is we can always take a stress element, okay, out of this location at here. So you can always take a stress element, okay, and then on that stress element, okay, and you will have a tau. You will have a tau at here, and you will have a sigma at here, right? So that's your tau here. That's your sigma. So basically, tau and sigma is this. And if I use DE theory, one mid-size stress, so I can calculate one mid-size stress. Right, that's the formula for mid-size stress here. So you can calculate one mid-size stress for this particular stress elements. Okay, plugging the tau and a sigma into this formula here, and we'll be able to get a sigma prime. Okay. Good. So you can do that. I'm not going to write it down here. So this is the relatively long expression. But if you plug in the sigma and the tau here, you get a sigma prime formula. Okay. So now the next step is, if I wanted to know at which angle that the theta, at which angle theta to make the sigma prime become maximum. So what do we do, right? Mathematically, you take derivative sigma prime with respect to theta, and then you set it equal to 0. That's how you find the minimum maximum, right? The critical point, basically. Okay. So if you do this step right here, and you'll find the theta equal to 62.5 degree, okay, will give you the critical point or the critical condition. And for this particular angle, my one mid-size stress sigma prime will take a maximum value, and the maximum value for the one mid-size is 2.16 times F divided by HL. Okay? Yeah. So that's the maximum one mid-size stress at the particular angle 62.5 degree. Okay. And similarly, at this angle here, you could calculate the shear stress, which is 1.196 F times divided by HL. Okay. So similarly, you can get the tau value, okay, for this one here. And similarly, you can also get sigma value here. Okay. Yeah. So you see the good idea now. That's very analytical, right? You want to get to the maximum value, and this is how you mathematically approach to find the corresponding theta angle that gives you the maximum value. So similarly, I can also forget about, if I forget about the one mid-size stress, if I just look at the formula for the shear stress, okay, just the formula for the shear stress here. So we could do this here. So we could just calculate d tau over d theta and let it equal to 0, and then solve for theta here. So this time the theta actually is different. It's got a 67.5 degree, and that gives me a tau max at here is 1.207 F and over HL. And if you plug in the plugging this theta value into the sigma, and you get a sigma also a maximum value, you get 0.5 F over HL. But this is actually because this is actually smaller than tau, so we don't really have to worry about this. But this is something we're going to have to use to compare. Okay? So that's analytical approach here. Okay, analytical approach. So even though I write so many for the analytical approach, now good thing is we're not going to use this. Okay, so the results out of the analytical approach here, so we actually won't use it because the limitations here. So there are limitations, okay, on theoretical results. So basically, experimental analysis show that no analytical approach can consistently predict existing stress. Okay, and so unfortunately, this analytical approach, the results of this, we cannot use it in general for every other basically situations there, right? So what do we do at here is we actually use a so-called conservative approach. Okay, so conservative approach. Okay. Yeah. So this is actually the approach. The results are listed here will actually be the approach that we're going to use, okay, for the future computations. Okay. So what's a conservative approach? Conservative approach basically means is we explode all of the force to the shear area. So I'm going to write it down here. So basically assume so all force applied to the throat area. Okay, to the throat area. So what does that mean is basically if this is the same location of the joint and we're doing the cutting, right? We're doing the cutting for the fillet joint. Now this time we're going to cut it basically 45 degree at here, okay? 45 degree. Yeah. So if you cut it 45 degree, then this portion here is, remember, it's called the T, and that's the throat, okay? And that cross-section area is the so-called throat area. Now if you have a force over here, F, then forget about the normal force, forget about this shear stress force. Let's explode the whole F to the cross-section area, okay, as a shear force. Okay, so that's the conservative approach. So assuming all the force, which is the F at here, will be applied as a shear force to the throat area. Okay, that's a conservative approach here. Now, how does that affect? So let's say this is H, the leg height at here. Then what will be the calculated stress, right, based on this approach, conservative approach? So here's a simple calculation in here. So what we do is let's calculate basically the stress. In this case here, all we have is a shear stress, right? So shear stress equal to F divided by the cross-section area, which is the throat area. And the throat area is T times L, right? The throat is T times L. And the T, because this is a 45 degree cut, so 45 degree cut. So it's like you have a basically a triangle. Okay, you have a triangle at here, 90 degree at here, and 45 degree at here, and this side is H, this side is a T. So the T value is what? 0.707 H. Okay, that's your T value. And then you times L at here. Okay, so you get basically the shear stress, okay, at this area. Good. And that's actually the simplest equation in here for the shear stress. Simplify a little bit at here. Okay, you use the numerator divided by 1 divided by 0.707, so 1.14414 times F divided by the HL. And so that's your shear stress, right? Shear stress. Okay. So basically at here, the conservative model considers only shear stress exists at the throat area in the fillet weld. Okay, that's conservative model. Now, why is it conservative, right? Why is it conservative here? First of all, let's compare this result with the maximum shear stress when we derive the analytically. What do you have here? You analytically get a 1.207, right? And what's the conservative here? It's 1.414. So that actually is even bigger than the analytical results there, right? That's conservative. And second of all, remember we also calculated the maximum von Mises stress at this angle here, which is this, right? Now, if this is the stress condition, then basically this is the pure shear, right? This is a pure shear loading. And I can still calculate the von Mises stress, which is just a √3 times tau. And that gives me √3 times this, that gives me 2.45 F over HL. If I compare this one with the maximum von Mises stress, that's also bigger than that, right? Yeah. So basically, this is why this is a conservative here. Okay. Yeah, this is a conservative model right here, and that's what we're going to use for our future calculation in the stress system. Okay. Yeah. Okay. So once we set down the common sense, okay, the common basically fronts for the calculation. Okay. So let's take a look at basically two specific situations for calculating the stress within a fillet weld. Okay. Yeah. So what are the two specific situations in here? So I'm going to look at the two cases. Okay. So case number 1, and then there's another case here. Okay. So any questions so far? Okay. So let's look at the first case. This first case, I call it, okay, shear in weld from in-plane torsion. Okay, in-plane torsion. Okay. Now this is a part that a lot of people actually get confused, okay, in the final exam actually. Okay, I give you a weld type of question, and a lot of people confuse this in-plane and then the second case, which is out of plane. Okay, so you'll actually see what's the reason here. So what's the in-plane here? So I'm going to give you a drawing right here. So let's say I have a base metal member right here, and then here's what we want to do. We want to weld another plate, okay, to the bottom plate at here. Okay, so let's extend this a little bit here. Alright, so this is what I wanted to weld this thing here. So let's say I wanted to do a welding like this. I do a fillet weld. So basically one weld on the top and then another weld at the bottom here. Okay, so a fillet weld on the top and the bottom. And here's the loading condition, F. And I'm interested in basically the stress existed inside the welds for this case, for this situation. So how do I do this? How do I do this then, right? Yeah. First step, let's do a free body diagram for the situation right here. Okay, free body diagram. So if I draw the draw this plate out. Okay. So let's say, suppose this is the center. Okay, so this is the center of the, this is the centroid of that weld group at here. Okay, the centroid weld group. Then for this weld group at here, so well, actually I shouldn't draw the plate. I'm going to draw the weld group at here. Okay, I'll draw the weld group. Okay. So let's say this is the weld group right here, right? Here is the center of the weld group, okay, the centroid. Yeah. Now, because of the F at here, what type of loading exists for the weld group? Because the F, you would have what? You would have basically kind of force basically for everywhere, right? For everywhere along the weld group, you have a force basically going down, isn't it, right? Yeah. And then also, the F will cause a rotation, trying to cause a rotation, right? So the F basically will cause a moment or torque with respect to this weld group. So if you use F times this distance, right? If you use F times this distance, then you will get basically a moment at here, right? So which direction? Actually, the other direction. Okay, yeah. Or torque. Okay. So basically, what it means is for this weld group on the top and the bottom, if you have something over here, then you have something over here. Okay, yeah. It will feel two things. One is the force. Anywhere you have force going down. Another is the torque or moment generated by the F right here. Okay? Yeah. So now, and if you think about it, right? So let me draw this again and here. I'm interested, basically, I'm not interested in everywhere. I'm just actually interested in the location that give me the maximum, stress. Okay? Yeah. So which location actually will be the most critical location within this weld group there, right? Which location will be most critical? Well, according to the free body diagram, if you pick any location, right? If you pick any locations, you will have what? You will have a force acting at that location, okay? And how do I treat this force then? Remember, in the conservative model, right? When you have a fillet weld, it doesn't matter how the force is applied, you always explode that force to where? To the through area, right? To the through area. And you use that force to generate a shear stress, basically. Okay? That make sense? So basically, I can consider everywhere on the through area there will be a shear stress, the tau, caused basically by the F at here, okay, by the F. So that's settled down, right? And second of all, let's look at this M at here. Okay, even though I call it M, you can consider also as a torque. So the torque trying to rotate that welded group, right? Try to rotate the weld group. So technically, if you learned when we learned the shaft design or bar, what does a torque? What type of stress does a torque generate? Shear stress, right? Torsional shear stress. Okay, yeah. And torsional shear stress, the formula is what? T times R over J. Okay. So if you want a location, critical location, basically that critical location must have a what? Highest value of R, right? So the bigger R, then you have a higher shear stress here. So if you look at this one here, if you have a torque applied here everywhere, right? It's like a, so you have a TR over J. Where do you think that critical location is for the shear stress of this one here? Which location do you think is the most critical one? The corner, right? So basically the corner at here. And what direction is that shear stress due to this? What direction is it? So this is the radius at here. shear stress, the direction shear stress is always perpendicular to that radius. Okay? Yeah. So this location will have maximum shear stress. And every other location will have what? The same shear stress from here. So then basically the critical location will be at here. So there will be two shear stress. I would call it tau prime and tau double prime. Okay? And this is basically our critical location at here. And I will call the primary stress a primary shear as this tau prime, which is basically the F over A. Okay? F over the throat area. Okay? F is this, A is the throat area. Okay? And then you have the secondary shear, tau double prime. Now the tau double prime, you can see it's generated based on the moments at here. So I'll write a m here. You can write a t. Typically we write a t, but we can write m in this case. So m times r over j. So r is that radius over there, right? That radius. Okay. So that's the two stresses, basically in this kind of in-plane at here. Now, did you get the idea of in-plane now? So what does in-plane mean actually? Why I'm calling it in-plane? So what do you mean by in-plane at here? So you see that this is the weld group at here, right? This is the weld group, and this is the force at here. What's the relationship between the F and the weld group? They are actually what? In the same plane. Okay? In the same plane. This is called in-plane here. Okay? And the next we're going to have a so-called out-plane, and you'll see the difference basically. Okay? Okay, so coming back here, right? If you get the tau prime and tau double prime, so technically the next step what you need to do is you need to basically create a vector to calculate the resulted shear stress, isn't it? Right? You need to calculate the resulted shear. But calculating the vector, they are not necessarily perpendicular in this case here. So it's hard to predict, and basically it's hard to calculate for this tau double prime and here. Okay? Yeah, and the vector here. Okay? Yeah. So what we do is we actually wanted to do is we do this. So I'm going to redraw this a little bit here, just to have a better drawing. So what we wanted to do is we wanted to have a little bit easier calculation. Okay. So I see the tau prime at here. I'm going to separate the tau prime to two different components. Okay, at this location. So I'll call this is tau double prime. Let's tau double prime x at here, and then here let's call it tau double prime y at here. Okay, and then there's one more tau prime, which is over here. Okay, so I'm going to separate the tau double prime into two different components. One horizontal, the other is a vertical. So how do I calculate if this is a centroid here? This centroid at here, how would I calculate tau x double prime? Here's the bending moments, right? Here's the torque. And the torque, how do I calculate this tau x double prime based the torque m? It's still m times a radius, right? But what radius now? See, previously this radius r. Which radius now for the tau x double prime? This portion, right? Good. So for this portion here, let's call this is let's say, I don't know, let's call this is a at here, right? Yeah. So m times a over j. And then similarly for tau y double prime, what would it be? It's m times this portion B at here and divided by G, right? Divided by G. So that's, in terms of calculation, same thing, but it will be much easier for the next to find the combined shear stress, right? So now if I want to find combined shear stress, what would that be? Basically, I would calculate tau equal to tau x double prime square, then plus tau prime plus tau y double prime square, and then square root. Okay? Yeah. So that's basically much easier, right, than calculating your original tau prime and tau double prime at here. Does that make sense? Yeah. So the last point here is, how do I calculate the J? Okay, the J at here. So J refers to basically the polar moment of area, okay, for this geometry, okay, this group of geometry at here. Okay. Now, to calculate the J, okay, so what we're going to do is we have a shortcut at here in terms of J calculation. So we're going to use a table. We're going to use a table 9-1, okay, for J. Okay, table 9-1 for J. Technically speaking, table 9-1 is actually doesn't give you the J directly. So table 9-1 gives you a so-called JU first. Okay, JU. So JU is called unit, basically second polar moment of area. So JU is called the unit, okay, second polar moment of area. Okay. So I'll show you what this table 9-1 is, and I'll tell you how to get J from JU. Okay, so this is the table 9-1. Let's take a couple of them here, just not a whole table into. So let's just take this portion in here. Okay. Okay. So as you can see, for example, right? If you have just one weld like this, okay, and it doesn't have any thickness, it's just one, like a unit, basically a single line here, right? Just a single line here. So that's why it's not a J, it's JU. Okay, and if you have a single, or you have a like a weld group like this, then the formula for JU will be this. Okay, and the table also give you the centroid location, X bar and Y bar, for that weld group, geometry group. So this is the unit single area. So once you get the JU, and the J is equal to 0.707H times JU. 0.707H is basically the throat area T. So here, what is a unit? Basically, is consider a unity throat area 1. Right? So this table. The actual throat area is 0.707 times H. Then that's why you use the 0.707H times the result JU at here to give you the J. That makes sense? Okay. So, for example, right, for this particular case, I got two horizontally parallel weld group right here. Okay, horizontal fillet welds here. Which one should I use to find the JU? But this is different. This is vertical, right? Doesn't matter, basically. The question is, this is the polar moment area, right? This is the polar moment area. So when it's the polar moment area, so this one here is equivalent to this. Okay, it's equivalent to this. Does that make sense? Yeah. So if I relate to this one in here, right? So you can see if I have a dimension, this is a B, this is a D. So make sure the B is the width between, okay, the width between the two welds, and D is the length of the welds at here. Okay. Now, if I relate it to this question, to the calculation of a tau x double prime and tau y double prime. So, for example, right? So let's say if I have it here, this is B, and this is D. Okay, this is D here. Okay, so if I have an M at here, okay, but M at here. So can you tell me what is tau x double prime? What is tau y double prime? Actually, I don't need you to tell me GU, because GU is already given. Then you time 0.707h, you'll get that, right? Yeah. So basically, what I want to say is M times what at here for tau x double prime over G, and M times what over G for the tau y double prime. The first one, what's M times what? 2 B over 2, that's right. And then here is D over 2. Very good, right? Yeah. So that's exactly that you have to be able to identify, okay, based on the given geometry and the dimension. Okay? Yeah. And I'll finish the other autoplane next week, and also the joint stability next week. Okay? Yeah. Any questions? All good? Yes. So, well, the thickness here it depends on what you're saying, right? One is the leg height H. One is the throat area T. You're talking about H? Yeah. So, come here. Yeah.